transfer function continues from yesterday. Yesterday I had something on the blackboard which I think we should have in front of our eyes all the time. So what I had was, if you have an image, and this is the image F, and this is our atomic structure. So let's say we have one atom here and one atom there. Yeah? And this would be our atoms. And we convolute that with another function, g. And this is our point spread function. And this is what the microscope does to the atoms. Then you get our image. And the image, especially if you defocus the electron microscope a bit, does not show you one atom and one atom. Only a CS-corrected microscope with Sharp focus would do that. But in biology, when you defocus to improve the phase contrast, what you see instead of this is some funny ring structure from the defocusing. And what happens here is that you have your atoms and it's convoluted with your point spread function, which has this profile. Yeah? So, and let's say we have three atoms. Another one is here a stronger one, a bigger one. Then the convolution would here produce another set of point spread functions, and they may actually overlap. So if they're a bit bigger, so then they overlap. And this is our image. So this is F convoluted with G, and it's the image. So and this is the image, and then you have this, and you do all your image processing, and you get rid of the noise and so on. But then you have this, and now the question is, what is this? Is this how my structure looks like? Or is it actually still the point spread function in there? And I need to get rid of that to do this. And yesterday, when we spoke about the Fourier transform, we said we can Fourier transform this into a Fourier transformation capital F that has whatever structure it has, the Fourier transformation. And this is multiplied with the Fourier transformation of this, which is the Fourier transformation of this thing, whatever that looks like. It's capital G, and it's only one multiplication, which is computationally much faster than the convolution. And this gives you another Fourier transformation, which then has another funny structure there. I don't know what it looks like. And this is F times G multiplied. And when you back transform this, so this would be the Fourier transform, and this is the Fourier transform, and this is the Fourier transform minus 1, the inverse transform. Then you are back here. Yeah? And now what we have is we record images, and what we want to know is the atom structure. Yeah, the sample. And in between is the point spread function that takes our atoms in the electron microscope to make the image. And you can also speak about this as that your Fourier transform of the atoms is multiplied with your contrast transfer function. This thing is the contrast transfer function. Yeah? And it's multiplied with your Fourier transform to give you the Fourier transform of your recorded data. We will come back to this. So a transfer function is a function that transfers, or that describes how our machine records data and transfers it to the recording media. Here's another transfer function, which is the transfer function of the subwoofer, loudspeaker. We have music recorded on a CD, perfect music, and then you want to transfer this into sound, into our ears, and this transfer function here describes what this lousy speaker does to it. And it's good at low frequencies, but at the high frequencies, it's really bad. Yeah, so the high frequencies, bird sound, so you would not be able to really well understand with this speaker. Maybe a little bit, but it's far too low. Yeah? So the perfect transfer function is 100% flat for bass and treble in all frequencies. Yeah? That's for sound. For electron microscopes, the transfer function looks absolutely pathological. perfectly would be 100% for low frequencies and high frequencies until we reach the resolution limit. But in reality, the electron microscope is close to zero, the phase contrast transfer function at low frequencies, then goes to some acceptable level, but then falls down to zero, and then even becomes negative. Yeah. And then finer, smaller things are invisible again, smaller things are white again, and then invisible, and then black. So this is what the microscope does to us. And then, so if I would be now this atom structure, and I would sit there, and one would take a picture of me with an electron microscope like this, then the picture would have a low resolution component, which is nothing arm, nothing belly, nothing arm. Yeah? And then this might be this frequency here, which is nothing arm, nothing belly, nothing. Yeah? And then the contrast is positive. That means you would have a picture that shows a belly and two arms, and then everything is okay. And then I have 5 fingers here, and these 5 fingers are closer together. That's a high frequency detail. And if you have bad luck, then the high frequency detail, depending on how I put my fingers, are just this frequency because they are closer together. And then the contrast transfer function is negative, and instead of having white, black finger, white, black finger, white, black finger, we have the opposite, which is black, white finger, black, white finger, black, white finger in the picture. And then you would take the picture and count and say that person has 6 fingers. Yeah? And then on the other hand, I put my fingers further apart, so then I'm here with my frequency, and then you would say on the other hand, the person has no fingers. And that's what your picture shows. So picture shows 2 arms, 6 fingers on one hand, and no fingers on the other hand. That's the contrast transfer function of an electron microscope. So this was all described by Otto Schalk, who was working in the 40s, 50s in Germany. And he had a few PhD students. One of them was Dieter Tübke, who was then with Wolfgang Baumeister for many years and was one of the main theoretical driving forces behind the development of electron tomography. And another of his PhD students was Harald Rose, who is in Münster and who is the driving force behind the design of aberration correctors, CS correctors. So these 2 leading figures in today's cryo-electron microscopy are still PhD students from Otto Schalk. And Dieter Tübke gave me a few pictures of him, even though he's retired now. So what happens in the electron microscope is that we have our sample, in our case a 2D crystal of membrane proteins, and the electron beam hits the sample. And most electrons, as Philip explained, go straight through and go onto our screen or the CCD camera or film. But some electrons, the good ones, they are scattered by an elastic scattering event to some angle, some scattering angle, and then the objective lens focuses them more or less back onto the same image location, and this path here is longer than the straight line. This is the shortcut, and this is the longer path. And so the scattered electrons, they arrive a bit too late, or they have a phase shift. And then what happens in the image is that the non-scattered and the scattered electron wave, they interfere, and they produce some phase contrast. That's an approximation. The reality is a bit more complicated. Anchi and Glaser would know that better, but this is one way to explain it. So now the question is, how much phase shift do we have here with a scattered electron beam? And this is what Otto Schalk calculated. This gamma function describes how the scattered beam comes later than the non-scattered beam. It's the phase shift, and it's dependent on the resolution. U is the resolution axis, the horizontal axis. According to Bragg's law, the resolution is also this angle here. Low resolution details are encoded by low angle scattered electrons, and high resolution details are encoded by high angle scattered electrons. Yeah, that's Bragg's scattering law. So we have a function that describes how the scattered electrons come too late, arrive with phase shift. And this is a function that depends on the wavelength of our electron microscope. Higher kilovolts, 300 kilovolts, has a shorter wavelength, and therefore this phenomenon is actually no. This is the longest. So here's another function. It's the wave aberration function. this is the full formula. And since this has a few, so lambda also in this, it turns up that lambda is to the power of 3 here and lambda is linear here. So higher kilovolts give you a shorter wavelength, and this gives you less wave aberration. And this is why 300 kilovolts have less problems with the contrast transfer function than 100 kilovolts. The Scherzer formula has two major terms. One is this one, which shows the resolution dependency on the resolution to the power of 4. And the other one is this one, which is to the resolution to the power of 2. And this later one is proportional to the amount of defocus that you apply, how much you defocus. And the first one is proportional to a constant. And this is the spherical aberration constant of your objective lens, of this lens. It's the error that this lens does. And this is Scherzer's formula that describes how the scattered electrons are phase shifted when they reach the image. And so this includes the CS, the spherical aberration constant. And the spherical aberration constant is for the objective lens a constant that describes the error that the objective lens does to the electron wave. Normally, an electron that passes the sample here can be scattered straight and then arrives here. But some electrons that are scattered to a higher angle, they are affected by defects in this lens, by aberrations in this lens, and this is quantified by this constant. And the constant is usually in the order of 2 millimeters or so. And the more problems the lens has in aberration, the stronger this constant is. And so instead of perfectly focusing our electrons to a point, the lens focuses the electrons so that higher angle scattered electrons are focused stronger than low angle scattered electrons. They are focused less. And this is this aberration. Our lenses also have a second problem, which is called chromatic aberration, which means if we have 300 kilovolts in our electron beam, they are not all exactly 300 kilovolts. Some are a little bit faster and some are a little bit slower. Yeah, it's 300,001 or 300 or 299,999 kilo electron volts energy. And these different speeds in electrons, they are focused differently. The fast ones are focused less and the slower ones are focused more. And the amount of aberration, depending on the speed or the chroma, the color of the electrons, is quantified by this constant. And usually it's also a constant that has the same magnitude as the CS constant, so another value of 2 millimeters or so. And these two constants, CS and CC, play a role for the definition of this formula that describes the contrast transfer function. So we have Otto Schalk's formula. There we have the spherical aberration constant. The chromatic aberration constant comes later. And this describes now the phase shift. And then in the image, we have an interference between the non-scattered electrons and the scattered electrons that come too late. And the interference pattern gives us a sinus function of the phase shift. And this is why we have this this oscillating phenomenon. So the more phase shift we have, the sinus of that is the contrast transfer function, which then gives an oscillating pattern. And this would be the phase contrast fraction. And then you also can calculate a cosinus of the phase shift, and that is the amplitude contrast that our sample gives us with a factor in front of that, and this is with a factor in front of the phase contrast. And this all gives us the phase and amplitude contrast transfer function. And this is all multiplied or enveloped by an envelope function. I will come to that later. So in practice, with a biological thin sample, as a 2D crystal is, we effectively only have to worry about this term here, and this is then 97% or so. And this one you can usually ignore, this is 7% or some lower percentage. So phase shift with a sinus gives you the contrast transfer function. And then, in the end, we have this envelope function. And the envelope function, so maybe I just write this down for the moment. So this function here, if I only look at the right half of this, we have the contrast transfer function, and that would be the resolution u, and this is the contrast transfer function. It's now the sinus of the phase shift. Yeah? This is more or less the contrast transfer function, but what you have now to do is still to put an envelope function onto that, and with envelope function, the contrast transfer function then looks like this, and this is then the resolution limit. This is the resolution, and this is the contrast transfer function with envelope. And this envelope function is a function that dampens our CTF like this, and this depends on many factors in the electron microscope. The general envelope function has different components that are all multiplied together. The first is ES, is an envelope function that is dependent on the angular spread of the source. Do we have a field emission gun that puts the electrons out in a very narrow direction, all parallel? Or do we have a lab 6 or tungsten filament that puts electrons out in every direction? Which is this alpha opening angle of the source here. And there's an equation how this then affects an envelope function. Then we have a chromatic aberration envelope function, which describes how our electron gun is putting out electrons. Is it 300,000 electron volts plus minus 3? Or is it 300,000 electron volts plus minus 1 electron volt? You can have an energy filter in there, then it's even less, so 300,000 plus minus 0.2 electron volts or so. And this delta E, and also variations in the current and in the objective lens current and the acceleration voltage and the current from the gun, all this gives you a chromatic aberration envelope function. Another envelope function of this type is when our specimen drifts or vibrates, and then our CCD detector would usually also dampen, effectively dampen the contrast transfer function of the entire microscope. So this is, for example, the envelope function of a CCD camera or photographic film. I have an Excel sheet that puts this all into practice. This is on our web server, ccina.org. So this is an Excel sheet where I put all these Scherzer equations, the sinus of the phase shift, and the envelope functions into a big table. And this is calculated here. It's just the resolution and then the phase shift, and then the sinus of the phase shift, and then all the different envelope functions, all the equations that I just had on the blackboard, they are all calculated here in an Excel sheet. And then this Excel sheet is used to show the phase shift that the scattered electrons get. So the non-scattered electrons don't get phase shift, we are at 0, but at higher angle, at higher resolution, there is phase shift that is more and more. And then the sinus of the phase shift gives you this oscillating function, and the cosinus would give you the phase contrast. And then this Excel sheet has constants here, where you can put in all kinds of numbers. So what acceleration voltage do you have? 200 kilovolts or 300? What is the CS, the spherical aberration constant, 2 millimeters? What is the defocus, 1 micrometer defocus, and so on, lots of other. All these blue fields are constants. And it's an Excel sheet. It's very simple. You just say, okay, we have a 100 kilovolt microscope, and we put it to 300 nanometer defocus. Let's say under focus, so minus 300 nanometer defocus. So, and then this is the contrast transfer function that you would expect. Yeah, and you would have good transfer at 2 nanometer or 1.4 nanometer resolution. You would have no resolution transfer at 1 nanometer resolution. You would have the wrong contrast at 0.9 nanometer resolution. And your microscope's resolution limit is probably around 0.5 nanometer or 5 angstroms. Yeah? This would be a CM100 or T12 or so. Or you say we go to Fujiyoshi's supermicroscope, then we have 300 kilovolts, and we have 1.6 millimeter CS, and we have a field emission gun, so a very narrow opening angle. And then we want to boost contrast, we defocus by 3 micrometers. Yeah. Then, minus 3 micrometers. So we have this. On your Excel sheet, is that autofocus part? Yeah, there's somewhere in the version. So this is a version of this Excel sheet that actually Victor Tsenou from the Ben Gurion University modified, and he must have inverted the contrast. But what he put in is the defocus spread, the focal spread here. And so if your objective lens or if your sample has some variations, I did not have this. This is why I use his version. So usually this would be my version, but it's slightly different anyway. So there's an Excel sheet where you can just type in the settings that you have on your microscope, and then see where is my Thon rings. Those are the rings we fitted yesterday in the practical. These here. What is the resolution limit, and so on. Okay, this is how this would look like. And I was speaking about envelope functions. The last envelope function was the CCD camera. And this is a graph that Richard Henderson sent me recently that compares the envelope function. This here is the resolution, and this is it's not the envelope function, it's the detector quantum efficiency, which is something similar. It's effectively the signal-to-noise ratio of your detector as a function of resolution. And it compares a CCD camera with film, D is film, and with a good CMOS detector like the Falcon or the K2 from Gata and the Falcon from FEI, or a future proposed fantastic detector that is under development. Yeah, so at the moment, film is much better than CCD cameras. CCD cameras and at high resolution fairly lousy. Film is better. Fabian yesterday told us his seminar, he used film. If you would have a Falcon detector, €500,000 or so, or dollars, you would be better than film. And with a future generation super duper detector, you would even be better. Yeah. So we lose a lot at the detectors. And this is all at 300 kilovolts. If you use 100 kilovolts, then a CCD is usually still acceptable. And I showed you this CTF simulation Excel sheet. So now, back to square one. We have our atoms in the electron microscope. In this case, it's just lines. So some viruses, rods or so. And then we switch on the electron beam and we make an image. And the image here is this thing. It shows an image of our structure, and that's convoluted with a point spread function. And you can also describe this as the Fourier transformation of the image is multiplied with the contrast transfer function. The contrast transfer function is the Fourier transformation of the point spread function. Point spread function in real space is contrast transfer function in Fourier space. And this would be a contrast transfer function, and the spacing of these rods or these lines would now correspond to this this resolution. And at the moment, we would have in this setting positive contrast. Now, if you sit on the microscope and start turning the defocus up and down, the defocus more and defocus less, then this would be a lot of defocus, and then you get closer to focus, and then you are in focus, and then you are over focus. This would be now over focus, where the contrast is inverted. Then this one frequency is sometimes positively visible, sometimes negatively visible, and sometimes invisible when you're just at zero. This is what happens in your microscope. But it happens to all frequencies if you have lots of different structures in your sample. It happens to all of them on the same time. This affects your image. And you can also see that a highly contrasted image is when you defocus a lot, so that you're just at a maximum. If you defocus too much, you are at the resolution limit, then you have nothing. And if you do not defocus, then it's also flat gray and you have nothing. So you need to defocus a bit, but not too much. So what you want is, ideal setting would be, for this frequency, would be probably here. Oops, I would have to stop this. So, well, I think you got the message. So we, stop this, and we want, I can't do it. Okay, we want this much of defocus for that frequency. Yeah? Then we have full contrast. There are different definitions what the contrast transfer function sine is. The mathematical clean deviation says it's a negative function, but I usually plot it positive because it makes more sense to me. So the sine is up for definition. So this is what we were dealing yesterday with. Yeah? So the Fourier transformation of our image, this one, shows these black rings. And we were fitting the zeros of the CTF. We were fitting this point and that point and that point with these lines. And you have seen that the position of these lines depends on how much defocus you apply. And so we are fitting the defocus here, and we changed the defocus values until these rings were exactly in the black lines. I think to be precise, the Thon rings are the white rings, yeah? And we are looking for the zeros between the Thon rings. But usually everybody calls the gaps between the white rings the Thon rings, which is fine. So if the position of these Thon rings depend on astigmatism and on defocus, then astigmatism comes into play in the sense that if you have astigmatism, then the lens has a different defocus in the horizontal direction than in the vertical direction. Or to be precise, there is an ellipse defined, and the ellipse can not only be horizontal or vertical, but also at a certain angle. The angle is defined here. And you can have 1 micrometer defocus in this direction and only half a micrometer defocus in that direction. And then you would have an astigmatism of 500 nanometers. Yeah. So this is what we did yesterday. So again here, the point spread function is in real space, is what our microscope does to the image when it wants to image an atom. And that's a convolution. And in Fourier space, it's a multiplication. We multiply our Fourier transform of our atoms with the contrast transfer function. And the contrast transfer function is the Fourier transformation of the point spread function. Yeah? So this is the real space description, and this is the Fourier space description of what the microscope does. So now we can come back to David de Rossier's summary. The Fourier transformation of a recorded 2D crystal picture shows us these Thon rings, it shows us the fraction spots, and it shows a lot of noise. And these spot positions with the lattice, we were fitting those yesterday, they give you the unit cell of your crystal and the unit cell shape. The spot size, if those are sharp spots or blurred spots, they show us how well the crystal is ordered. A perfectly ordered crystal will give you very sharp spots in the Fourier transformation. A badly ordered crystal will give you smeared out spots. Yes, maybe sometimes so smeared out that you don't find them anymore. The intensity of the spot relative to the background, so how bright is the spot compared to the background next to it, gives you the signal to noise ratio in your image. The distance of the furthest spot, out here somewhere maybe, gives you the resolution of your structure, of your data. And then if you go in with a computer and measure exactly the amplitude and the phase value of each spot, then later you can use that information to make an atomic reconstruction of your model, of your molecule. Then we have these Thon rings. The radius of the Thon rings is dependent on the defocus. So if you fit these Thon rings, then you find out how much defocus you had in your microscope. If the Thon rings are elliptic, then you have astigmatism. If you have somewhere absences, so you see Thon rings here, but you see nothing here, then you know you had some drift or vibration or so in the microscope. Yeah? We had that also yesterday. So, why is this all important? It's important because this is not how our atoms look like. We want this, but we have only this in the beginning. And now we have to get rid of this point spread function to do this. And this is what the computer image processing has to do. Yeah? So we record our picture, and then we want to deconvolute our point spread function out so that we have a map of the atoms. And now this will be a deconvolution step. There are computer algorithms that can do that. So they go here and we try to find what the point spread function is, and you try to search and if you can find your point spread function, and if yes, then you have an atom, and if not, then maybe not, but it's really complicated. And it's much easier, much faster for the computer to use this way. So you have your image and you calculate the Fourier transformation. That's what we have done yesterday. And then this one is your atom structure multiplied with the CTF, right? So this one just has to be divided by this, and then we are here. And then we back transform and we have it. Yeah? So now what we need to do is we have our image, we go to Fourier space, we divide this by the CTF, and we are done. So this is then contrast transfer function correction. It's done in Fourier space. This is our Fourier transform, yeah, Thon rings, diffraction spots, highest resolution, low resolution, and it's affected by the CTF. The CTF is positive, invisible, wrong contrast, invisible, and then there is resolution limits sometimes here. And we have positive contrast and invisible, negative contrast, invisible, positive contrast. These zones, so apparently 50 years ago or 30 years ago, people said the limit, resolution limit of the microscope is here, because this is all what makes sense, and then when the contrast is wrong, then you better ignore all this stuff because nobody understands that anyway. And Jacques Dubochet in the beginning said your resolution limit is here. When I started my PhD 16 years ago, he said the resolution limit is here because then it's so complicated it just makes headaches. But then actually, and also in Dubochet's time already, people said, well, there is still information here, we just have to correct this. And the easiest way of correcting this thing is by at least getting the sign right. So you go to Fourier space and you multiply your Fourier transform with a sign, an inversion. So you leave these pixels as they are, and then these here you multiply with -1. Here's -1 for this resolution range. And then, well, there's nothing, we can't help it, but these are okay, so we leave them as they are. We multiply with 1, and then this again invisible, and these again with -1. And so you have this +1, -1, +1, -1 that you multiply onto this Fourier transformation of the image. And then you back transform it, you have your CTF corrected image. Yeah? That's the simplest way of CTF correction, and it's called phase flipping, because you can either in Fourier space multiply this with -1, or you can also go in and take these complex values and add 180 to the phases, 180 degrees to the phases of these spots. It's the same thing. But that doesn't help us with this low contrast, high contrast, low contrast, invisible problem. So we can do something better. Maybe. So this one is another approach. You take your Fourier transformation of the image and you multiply it with the contrast transfer function again on top. So we have our CTF and we calculate the same profile and we multiply these two together. Then we leave these as they are. This area is multiplied with 0 and this area is multiplied with something negative. That works. We get this contrast right. So here the contrast is inverted. But we make this oscillation even worse. Yeah, so what was already dampened in amplitude is now even dampened further. It improves the signal-to-noise ratio of your final reconstruction, but it's not close to truth. Some people use this CTF-corrected image then to look for features, for particle picking, for example. And what we do in the MRC software is a Vina filter. So what this does is we want to take the Fourier transformation of the image and divide by the CTF. And so the problem is if you want to divide by this profile, you would divide these pixels by 1, that's okay. You would divide these pixels by 0.5, that's fine. You make them even stronger. But you would divide these pixels here by 0, and then your computer crashes. Yeah? So there's a problem. So you can't just divide by the CTF because it goes through the 0, and then you have a division by 0 error. And the Vina filter approach avoids that by saying we have our Fourier transformation of the image, and we want to divide it by the CTF, which is we multiply it with 1 over CTF, but we can't do this because we divide by 0. And to avoid this, you put the CTF on top and also at the bottom. That's still the same thing. So you multiply with the CTF and you divide by CTF squared. It's still the same problem. And then here you can add some constant. Yeah, and the constant could be 0.1 or something. And then, since this square is always positive and this is 0.1, you never reach 0 and you never divide by 0. And then your problem is avoided. And it turns out that the constant that you just have to add here should be the noise level in your image squared. Yeah, so you can put some reasonable noise level there and square it, and then put it into this Vina filter formula. And then what you do is effectively you divide by the CTF, but you never divide by 0 because this thing is always there. And your correction profile, this entire thing looks like this. So when you would here come close to the black Thon ring, then instead of going to infinity, it is limited to some reasonable value by this noise and then flips. And then you have this here all corrected with negative values. And this then gives you a more or less CTF corrected Fourier transformation where you have more or less a constant intensity all over the place, except when you are very close to these black Thon rings, then you're not perfect. Yeah. But this is the Vina filter, and this is done in the MRC software. But in the MRC software, it's not done so that you define a noise term here. It's done so that you say the entire correction factor is allowed to go maximally to 3 or so. There's a parameter in 2dx where you say how much maximum correction do you want to allow in these areas, maximally 3, a factor of 3, or maximally a factor of 5, but not more. You can adjust that maximum threshold as a function of the noise level in your image. Negative stain values images can support a higher correction, noisy cryo-EM images lower. So conclusions. The CTF, the contrast transfer function, defines the transfer of the contrast from the atom sample onto your image in Fourier space. In real space, you call this the point spread function that defines the impact of the image from a single point in the sample. So one atom is producing a point spread function profile in your picture. And the point spread function is effectively the Fourier transformation of the contrast transfer function. We have to understand the CTF and we need to fit it. We need to fit the Thon rings and the defocus, and then we need to correct it with a Vina filter correction. And then we're done. When we have tilted samples, then it gets much more complicated, and we will speak about that on Thursday. Yeah, for tilted samples, the problem is that on a tilted sample, the defocus is not 1 micrometer or something, but the defocus varies from 3 micrometers to 2 micrometer and 1 micrometer. And then the contrast transfer function for a tilted sample into the entire picture is a complicated beast, and we will speak about that on Thursday. So, that's it. Are there questions? Because if not...
You said the point spread function is the Fourier transform of the CTF, maybe it's the inverse Fourier transform of the CTF.
Right. Okay. Yeah. Yeah, because the CTF is in Fourier space and the point spread function is in real space, so it's the inverse Fourier transformation of the CTF. But in the formula for the Fourier transformation, I mean, it was this integral of f times e to the power of something. The only difference is the minus and the plus in back and forth Fourier transformations. But you're right, yeah. So this thing, convolution in real space, is multiplication in Fourier space. We will need that all over every single day for everything. Yeah? To understand the image formation, to do the image processing, cross correlation. This will come all over the place the whole week. So this is something we just should. We can just keep it there.
When the CTF has complex values, and how can you plot these complex values in the plot just behind you? You just take the cosine or the absolute value?
So the CTF is only real. It's just between 0 and 1 and minus 1. Except if you have beam tilt, then it becomes a complex valued function. Yeah, and then you get really into Devil's Kitchen, and then Anshi has to help you further because I don't know anymore. But Richard Henning said something like, if you have beam tilt, then your CTF is actually a complex valued function, where you have a phase gradient over your Fourier space in the CTF. So your pixels of the CTF become a complex valued function with an imaginary part. The phase of the CTF rotates around, and then Vina filtration, and so it gets very complicated. And Richard Henderson has understood that in the 70s and developed a method to correct it in the 70s in the MRC programs. And as far as I know, the MRC software for 2D crystals is the only software package out there in the world so far, in all disciplines, single particle, tomography, helical, and so, that can actually deal with beam tilt, fit it, correct it, get rid of it, and accept it as a fact and just deal with it. No single particle software knows what beam tilt is yet. E-Man, Spider, Imagic, nobody of those can deal with beam tilt. But Richard Henderson did it in the 70s. I'm sure it doesn't take long for the other software packages to pick that up. Is it right what I'm saying? Yeah, so it will come soon. And I think people like Hong Zhu and Holger Stark, and so they are all implementing that now into their single particle solutions. But so far, Richard Henderson is 40 years ahead of the rest of the field. Yeah. By having understood that beam tilt puts complex valued contrast transfer functions into practice, and he even implemented in auric tilt how to deconvolute that. Yeah. So I have the biggest admiration for his creation in the MRC software there. It's the one way would be to just go and say what is the signal to noise ratio. So how strong is my spots or all spots summed up compared to all the pixels that are outside of the spots? That would be a measure for the signal to noise ratio. And I think in 2DX we even have somewhere a point where it calculates that. The intensity in all the spots divided by the intensity of all the background pixels. That's the signal to noise ratio in your dataset. But in the MRC software, instead of doing this, Richard Henderson just divides by the CTF, and when this gets too close to 0, then it just cuts it off at a constant value. So Richard Henderson doesn't do this, he just... yeah? Okay, DQE here, resolution dependent DQE. Yeah, okay. You're right. Yes, exactly.
You would have to know anything at the resolution range.
Yeah.
Just one comment. I mean, the dynamic focusing for when you try to propagate, this is actually the big advantage of it, right? That you don't have to deal with the complicated CTF.
Yes.
But that's actually the main reason why you should be.
Yes, that's one reason. The other reason is that yes, that's this famous animation. So here, when you defocus a lot, you're not only changing the shape of the CTF, but also of the envelope function. And when you defocus a lot, then your resolution goes down. And so if you have a tilted sample, then this is, for example, the ideal defocus. And here your CTF looks perfect. Here it's too much overfocus, and here you are in focus, or too much under focus. And then here you have bad resolution in addition, because you have a strongly defocused microscope like now, and then the resolution of the machine is actually in that area of the micrograph quite bad. So that's another advantage.